a doctoral student at Center for Photonics and Computational Imaging, Institute of Physics, University of Tartu, Estonia. In this video, I am going to share about our recent research work on interferenceless coated aperture correlation holography for 5-dimensional imaging of 3D space, spectrum, and polarization, or we can say 5D ICOs. Developing holographic system that can encode information from a multiple dimension in a single hologram and reconstruct into a dimensional specific information is a challenging task. Such systems are often complicated, involving multiple optical and optoelectronic components. Also, such multiple dimensional systems require several camera recording, making them not suitable for recording high speeds events. In our research group, we have been trying to achieve 5-dimensional imaging techniques along 3D space, spectrum and polarization in ICOs with a single camera shot over the past years. We successfully developed a 5D ICO system recently. Unlike the previous researcher with the requirements and challenges, as I pointed earlier, our 5D ICOs requires only a single special light modulator and few optical components and require only a single camera shot. The optical configuration is shown here. Light from an object is incident on a coded phase mask, displayed on a special light modulator, a 4F system comprising two refractive lenses with the same focal length f project the complex amplitude after the SLM on an amplitude type diffractive optical element. The light modulated by the DOE is recorded by a monochrome image sensor. The above 5D imaging is implemented in a single camera shot, given that an extensive PSF library along depth, wavelength and polarization has been recorded once and stored in a computer. The proposed technique exploits the polarization-dependent light modulation characteristics of a special light modulator to record polarization-dependent intensity distribution, which are distinguished by a significant blurring between the orthogonal polarization states. 5D ICOs is implemented by interconnecting all 5 dimensions in a single frame, and image recovery is attempted from a different configurations of recorded point spread intensity distribution and a response to the object intensity distribution along 5D using recently developed deconvolution techniques. The proposed techniques can be useful for birefringence microscopy and functional and structural imaging applications. Now let us discuss about the simulation study. The simulation study was carried out using a MATLAB software. For the demonstration of 5D ICOs, in this study we choose a spiral lens with a topological charge 5 and also a binary random lens, as this combination enables maximum discrimination between the two polarization states. The goal is to obtain maximum discrimination between the orthogonal polarization state, in addition to having a high throughput from the object to the image sensor, which is desirable for any imaging system. So for the case 1, when the light from the object is polarized along the active axis of the SLM, it undergoes two modulation, one at the SLM and another at the DOE. And in the case 2nd, when the light from the object is polarized orthogonal to the active axis of the SLM, the light from the object undergoes only one modulation, which is at the DOE. In principle, even if the same diffractive function are used at the SLM and the DOE, the resulting intensity distribution will be different for the two orthogonal polarization cases. The goal is to design an amplitude-only QRDL with a controlled scattering and a focal length where the scattered pattern has the smallest area. The design is achieved using a GSA algorithm, which is a Gerg-Sexton algorithm. Now I want to discuss about the simulation results. Two test objects, namely the CIPHR logo as object 1 and the logo of University of Tartu as object 2, were used as the test objects for the two polarization states. 0 and pi/2 is shown in first row, first two images, and the phase and the amplitude images of the two diffractive functions are shown in the last two images of the first row. In the second row, the first two images show the IPSFs for the 0 and pi/2, which are calculated when both functions are activated and only the amplitude function is activated. In the last, the response to the object intensity distribution IO with polarization state 0 and IO with polarization state pi/2 of object 1 with IPSF of polarization state 0 and of object 2 with IPSF of pi/2 is shown. In the last row, the reconstruction results of autocorrelations and the cross correlations are shown. Now I want to discuss about the fabrication of the passive diffractive optical element. For the experiment, the QRDL was fabricated on a barium fluoride substrate via photolithography in ISO5 clean room. Positive photoresist was spin coated, baked, exposed using a maskless agar and developed with a AR 300 to 44. After oxygen plasma treatment, Ti and Au layers were deposited via electron beam evaporation with Ti enhancing adhesion. The lift-off process in warm acetone finalized the QRDL, suitable for visible to infrared application. Now I want to discuss about the experimental setup. For the experiment, we use a high-powered green LED from Thor Lab was collimated using a 7.5 cm focal length lens and controlled by iris 1. The collimated beam passed through a linear polarizer. Light from the pinhole and object was collected by a 5 cm lens and iris 2 and then directed to the SLM. On that, a spiral lens of topological charge 5 was displayed on the SLM. The reflected beam was projected on the fabricated QRDL using a 4F imaging system in which two lenses having focal length 7.5 cm and 10 cm is used with the magnification factor 0.75 before reaching to the image sensor. Now let us discuss about the experimental results. The experiment was carried out to demonstrate the results into 4 steps. In the first step, the polarization-dependent eye coach is demonstrated. In the second step, 4D imaging capabilities in 3D space and polarization were investigated in eye coach. In the next or the third step, 4D imaging in 2D space, spectra and polarization were investigated using eye coach setup. And the last or the final step, 5D imaging along 3D space, spectrum and polarization was investigated. So let us discuss about the first step. In the figure, column 1 shows the point spread intensity distribution. Column 2 shows about the response to the object intensity distribution were recorded using a pinhole 100 micrometer and the object O1 which is digit 2 and the object 2 which is digit 3 at two polarization state. One is at 0 and another at pi by 2 and two depth. One at 5 cm and another at 6 cm respectively. The corresponding reconstruction results using the algorithm LRRA is shown in column 3 and the incoherent nonlinear deconvolution using an iterative algorithm results are shown in column 4. As we can see from the results that the result corresponding to the IPSF and IO at the same polarization states results shown corresponding to the first two rows depict that the image of the objects has been reconstructed, and for the last two rows for the cross polarization state the image of the object is not reconstructed. So in the second step, the 4D eye coach IO at two polarization states 0 and pi by 2 and two depth 5 cm and 6 cm separated by 1 cm were computationally stitched into 2 cross 2 matrix and reconstructed with the recorded PSF. So in column 1 of figure shows the stitch matrix, column 2 shows the IPSF and column 3 presents reconstruction results using LRRA. It is evident from the reconstruction results column 3 row 1 and 3 that for the polarization state 0, objects at the both planes are recovered from the point spread intensity distribution at plane 1, that is IPSF at Z5 cm. Similar results were obtained for the point spread intensity distribution at plane 2, that is IPSF at 6 cm. Rows 2 and 4 of column 3 show the reconstruction results for polarization state pi by 2, and figure clearly shows that the reconstruction results of the object images with the IPSF of orthogonal polarization state is not possible. However, the reconstructions of the object images with the IPSFs of different depth cause only blurring. The reconstruction results of O1 in row 1 of column 3 is sharper than the reconstructions of the O1 in row 3 of column 3. Similarly, the reconstruction results of O2 in row 3 of column 3 is sharper than the reconstruction of O2 in row 1 of column 3. Let us discuss the third step in 4D eye coach imaging, the experiment with the green having wavelength 530 nanometer and the red having wavelength 660 nanometer, LEDs recorded IO and IPSF at two polarization states, which is 0 and pi by 2. These recordings were computationally staged into 2x2 submatrix for each wavelength and polarization, forming a 4D matrix, and reconstructed using LR array. In the figure, the results column 1 show the synthetic submatrix, column 2 displays the IPSF, and column 3 presents the reconstruction results. From the results, it is clearly shows that the IPSF of the green LED recovered the object information recorded with the red LED, and vice versa. As demonstration in the previous iCode studies, however, when the polarization states is not matched, there is no image reconstruction, indicating strong polarization discrimination. So in the last and the fourth step, the final experiment explored 5D iCodes imaging along 3D space, spectrum and polarization. IO was recorded at the two polarization states 0 and pi by 2, two depth 5 cm and 6 cm, and the two wavelength green and red, and the computationally staged into 2x2 submatrix, each representing a unique 5D combination. In the figure, right hand side, present these submatrix in column 1 and the corresponding IPSF in column 2, and the LR array reconstruction results in column 3. So from the result, it demonstrates the strong discrimination in the wavelength and polarization, with unmatched condition yielding no reconstruction, while the depth discrimination caused mild blurring. Depth, wavelength and polarization specific information was retrieved from a single recording. In conclusion, we successfully demonstrate 5D iCodes integrating 3D space, spectrum and polarization for the first time using a single camera shot, leveraging the polarization-dependent light modulation of SLM with phase mask, spiral lens and QRDL. The technique achieved polarization and the wavelength-dependent image reconstruction with a high temporal resolution, while the strong polarization and the wavelength discrimination were demonstrated. Challenges such as the low SNR, optimization of diffractive elements, and the advanced computational methods, including deep learning, and can address these challenges. The studies limited at the two polarization states paved the ways for expanding to the additional polarization orientation and 6D imaging in future, making it a promising tool for birefringence microscopy and functional imaging application. So in the last, I want to thank my supervisor, Professor Vijay Kumar Anand and Professor Ayla Tam, and also our collaborative professors, Professor Joseph Rosen, Professor Solius, Professor Kaupo, Dr. Tatsuki Tahara, Dr. Arne, and also my colleagues, Dr. Vipin Tiwari, Agnes, Tauno, for their invaluable contribution in this project. So thank you so much, and we will meet in the next talk. Thank you.